So our first session this morning is about self-driving, but more specifically today's and tomorrow's self-driving. Yesterday we talked about the origins of self-driving at CMU. Today we're going to talk about the current self-driving that emanated from CMU. And by the way, my marketing department, Raj Reddy, told me to mention to everybody the slogan, right? CMU is the birthplace of self-driving, remembering yesterday the 1983 project, Autonomous Land Vehicle, okay? So remember that when you meet people, okay? CMU, the birthplace of self-driving. We'll send an email. We'll send an email with the logo in the CMU palette. How is that? Okay. All right. Okay. So more seriously, let's go to our panel of two speakers representing two companies that came from the work here and the people here, more importantly. They are competitors, by the way, but they told me since we're on CMU neutral territory, we're going to behave, okay? So, all right. So Drew is going to go first.
Hey, everyone. I'm Drew Bagnell. I am lucky enough to have been part of the Carnegie Mellon community for, I think, 25 years now, quite a while, and serve as a consulting professor in RI. My day job, I'm a co-founder and chief scientist at Aurora Innovation, which is a self-driving vehicle company, and focused mostly on trucks at the moment, as shown by the video. So I couldn't help, in talking to Marshall and Pete, ending up doing something of a walk down memory lane. And so you'll see some things, maybe some things you've seen earlier or we'll see later at this. But I just wanted to chat about some of them. So the first thing I want to point out is that this idea of self-driving is not a new one. People have been thinking about self-driving vehicles for a very long time. This is a picture pulled from Scientific American in 1918, where people were imagining self-driving vehicles all the way back to then, probably before, but I think that's a kind of early date to date things. Then, of course, Chuck, do you recognize this video? Yeah, I pulled down this video of some of the early work in self-driving at Carnegie Mellon, the NavLab project, by many folks in this room, folks who worked on this, including Chuck, of course, and Marshall, Tony, and others. This vehicle went from driving through Shenley Park to, well, first we got to wait and see it not hit. I believe this is your son. And
obstacle avoidance for robot vehicles.
Amazing. And what you see in this is really the origins of kind of planning technologies and computer vision technologies that I think are the heart of what we do today. And then, of course, this went on to the highway. That was Dean Pomerleau. And this became, I would argue, the origin of the ADAS systems we have today, the Advanced Driver Assist Systems today. So CMU, the Robotics Institute, and Raj's creation of that really led to this origin of self-driving vehicles. It turned out I was lucky enough to work with Michael Nekiba, who was an RI grad and a University of Florida professor and founded Pittsburgh Pattern Recognition, on my first self-driving paper, which was a combination of reinforcement learning and imitation learning in 1999 with neural networks, back when they were called neural networks. And that was really fun, to get to combine these technologies back then. So I've been working in this area for a long time, it turns out. I think the big events that really got people thinking about the practicalities of self-driving were first the DARPA Grand Challenge and Red's work there, and got people very excited about this kind of off-road. And then later, the Grand Challenge, I think, really changed people's viewpoint. And this is, of course, the CMU team won this event, and it was a vehicle, as I think many of you know, on-road, navigating around, going from location to location. And I think people started to think, wow, maybe this technology could be commercialized in some way. I'm spending most of my time working with folks like Tony and Marshall on big outdoor mobile robots, And the real technique there, Pete as well, lots of folks, real technology there was getting machine learning, Dave Bradley. Dave spent a ton of time building the machine learning techniques that actually let this robot navigate around in really tough environments. And so we were really focused on how do we advance the machine learning technology so that the robot can understand the world around it. That was the kind of big push. And this was a lot of fun. We had a lot of fun getting these robots to go from point A to point B over like 10 kilometers between waypoint to waypoint. It was pretty neat. No moving obstacles, though. Very different than the kind of urban environment. So in 2009, Chris Urmson, who's my friend and co-founder, left CMU as special faculty to go off to Google to found what became Waymo. He's one of the founding team there, and he ran that program for many years. I was not yet convinced that this was a technology ready to go. What really convinced me, I was working a lot on kind of industrial applications, but what really convinced me that it was going to be time soon that we could commercialize this technology was two things. And the first was machine learning that started to really work. That was one of the biggest things. And so Marshall will remember some of these videos. We were able to take training data, people human annotating camera images, LiDAR, et cetera, and interpret the world. In this case, interpret LiDAR data from CMU and figure out where the buildings were in the world, where the trees were in the world. And you could do this, it turns out, from sensors on planes. You could do it from sensors on the ground. You could do it in multimodal sensing. So you could combine cameras and imagery. And in 2010, you could actually interpret the world and basically get it correct. And that was a big change. Having worked on these other projects, they were very hit or miss at the time. And that really changed about 2010. One of my favorites, this is the thesis work of Varun Ramakrishna, who runs the perception team at Aurora. He built the first system that could look at a still camera image or a video and figure out how people were posed in that image. Chris Atkinson actually went to his thesis defense and stood in front of a live camera and tried to break it as best as he could, and then said something at the end like, "Hot damn, computer vision finally works." If you know Chris, you can imagine that, I'm sure. What's really changed since then, all those things I'm showing you were pre the revival of neural networks. The big thing that's changed in that time is enormous increases in compute. Right? That's one of the biggest. Enormous increases in available data. When people realized, hey, wow, this machine learning stuff could really work, and the more data you throw at it, the better it works, people started getting a lot of data. Right? And then the reinvention and invention of techniques based on neural networks that can actually take advantage of that compute and take advantage of that data. That was kind of the big innovation. The other thing that really convinced me was the self-driving 1.0 products became real. So there's a number of folks, Stuart, Alex, that table, who worked on getting autonomous tractors out there, autonomous agriculture. And that's going to be an increasingly big thing. I was lucky enough to work on another self-driving 1.0 project, the Caterpillar effort. I don't know what the current stats are, but last I had heard, they had done something like 5 billion tons of ore with thousands now, multiple thousands of trucks that are notably safer than humans and are more productive and more profitable than humans at driving things. For those who haven't seen these trucks before, that's a big truck. It's a really big truck to be autonomous. So anyway, that was one of the things that convinced me. And so we founded Aurora to be the self-driving 2.0 company, starting with data, a data-first approach, and really building AI in right from the beginning. Took us a while, but we eventually figured out that the right market, turns out when you build a product, you have to build a product that's actually useful to someone, that they can make money and take advantage of. It can't just drive from point A to point B, it has to do something useful. So it turns out that long-haul trucking, which is about a $700 billion business in the US, is a very good market for this. It's a place where you can take advantage of utilization and do really well. What we build is the Aurora Driver. It's a combination of software, so the kind of intelligence to figure out how to get from point A to point B, the hardware, the sensing and compute that makes that possible, as well as data services like remote assistance and map priors that help the vehicle. That's the combination of things. We work mostly as transportation as a service, moving to driver as a service. And what that means is we do long-haul routes. Think in your head, Phoenix to Fort Worth, where cargo was being pulled and then taken from a terminal to a customer's site. Okay, and you're thinking of folks like FedEx as customers. Okay, and ultimately driver as a service, where the vehicles are actually owned by the folks like FedEx, and they operate the vehicles and drive it directly from their depots to other depots. I'll skip this except to say that turns out redundant sensors are really important if you want to get an actual product on the road. It's actually very helpful to have, in this case, state-of-the-art long-range LiDAR. You're thinking LiDAR that can see well past 500 meters, and taking advantage of frequency-modulated techniques, as well as combining that with high-definition radar and cameras. Just wrapping up the last couple slides, for us, one of the big things, and I'll linger on this at the end, is that it's critical to build a kind of virtual test or simulation or both infrastructure. In the old days, I remember very much in the old days, and many of the folks who remember that, if you wanted to test your robot, you made a change to some code, and then you put the robot out there in the field, and you saw what it did, right? And if it got better, you kept that change. And if it didn't get better, you reverted it and tried another one, right? Turns out that's not a great way to develop, right? The better way to develop is to treat your real-world experience as a way to build data and tests, and then almost all of the work you're doing is testing the system offline. And that's one of the things that I think has been the biggest change. And so I'm just showing an example here of, as an additional set of tests, the many tests we have in the system, we simulate the Aurora driver driving in all of the fatal accidents that happened over a time span, I think it was from 2018 on, in various operational design domains that we encountered. And what we find is that none of those accidents actually happen if you have a very attentive driver. And that's that's a full simulation of the sensor data coming into the system, as well as the driving and decision making of that system. And so I'll linger on just a last slide of, Marshall asked me to talk about lessons learned. And I think I came up with 3 that were what I've pulled out of my time working on this. The first is that autonomy is fundamentally a data problem. By that I mean a number of things. One thing I mean is that what gets all the attention academically is algorithms and model structures and things like that. Turns out those things are nice and they're fun and you can make advances, but what really matters, 80% of the work, is in data. So it is in gathering, managing data, the quality of the data. I have reliably seen every time we improve the quality of our data at Aurora, performance goes up. Those are almost always the biggest bumps in performance for us. The quantity of data, quantity has its own quality, as they say. The variety of the data, that it covers lots of things, and dealing with distribution shift, meaning the vehicle's own actions affect its own inputs, those kind of things. Simulation and virtual testing. I'll also say that another thing for me is that over time, the difference between tests and data have become, it's very hard for me to tell the difference. They look very much the same to me. And in fact, many of our tests, their success criteria are also data-driven. And it's kind of data all the way down. So what it means to pass a test turns out to be decided by a learned model. That learned model is also trained on data. I already mentioned the simulation and virtual testing. There's a quote that I've heard attributed to a number of people, but notably to Keio Kanade, that simulation is doomed to succeed. I think that's true in a sense, but if you can't make your system work in simulation, it's sure not going to work in the real world. And so simulation in this kind of virtual test environment is I think, the key to accelerating robots. And I might be channeling Chris Atkinson here again, but I would say almost everything I've seen that actually works is model-based. So there's some kind of model or simulation of a system, and that's what's being used. And the final point I'll make is that autonomy alone is not a product. What you find is that, for instance, there's a trucker in a truck, and mostly what they do is drive from point A to point B, but they do a lot of other things on both ends as well, and sometimes in between. And to deliver a product, you have to fill all of those gaps. So you can't just sell autonomy as a thing. You have to actually meet your customers' needs. And so those are the kind of 3 lessons I would linger on. And then I would end on a video. I don't know, Marshall, do we take questions at the end, or what do we do? That sounds good. This is just a video of going from Houston to Dallas, just showing you what it looks like for the Aurora driver as it goes. And it's fast enough that you can see it in a couple minutes, but I'm going to turn the podium over to Pete.
All right, I'm Pete Rander. As you can see, I have a lot of connections to CMU. I decided to list everything I could think about. And it's been interesting being in the university as a student, fighting that master step to get to PhD. I did reach the classic point. There are no students here today? Oh, good. All right, we have at least one. All right, well, I'm talking to you. Oh, yeah, wait, a couple. I reached that critical point where I'm like, good Lord, I don't see a possible way to get a PhD. Takeo, just tell me, go. And he had another idea. And it's that one idea was the thing that's like, okay, because I'm just like, I must not be cut out for this. This is awful. So got the PhD, then we did a little startup, and then anyway, we'll get into this discussion. But anyway, I acquired a lot of roles before leaving the university, and we'll get into that. What I want to do first is bring you back to my first time my illustrious introduction to self-driving. So you have to go back to the year is 1991. That's when that's my introduction to this. I'm at the University of Detroit Mercy. I'm a senior there, and I have applied to CMU. And I am eagerly awaiting to hear, maybe I got my NSF grant or something like that in there too, and that was circulated around, and I'm hoping maybe somebody will let me know. Well, there I am, I'm waiting, I'm hoping to be contacted, and then the phone rings. Yeah, that's the style of phone that was in the dorm room, you know. For all of you students, it's like this concept, remember, this was new, much newer. And so phone rings. So what do I get at the other end? I get this person saying, "Hi, my name is Professor Takeo Kanade," and probably all of you have heard Takeo talk, and it's pretty good English, but I'm like, oh boy, all right, what did he just? Okay, I'm not. Can I remember that name? All right, doing all this, and he says you wrote about. It turns out it was Kohonen self-organizing neural networks. I'd done some. Rather silly project, I would say. In modern times, you'd look at this and you guys would say, but didn't you do this in high school? But at the time, it was an important little project in one of the classes I was taking. And he's like, and you wrote about this and how excited you were about neural networks. He's like, that's interesting because I have this PhD student who's using a neural network in his PhD work. And I'm like, oh, yes. You know, I'm thinking, remember, it's thankfully no Zoom, as you will see as I step through this. But I'm hearing this. He's oh, there's a PhD student using a neural network to do this. Like, good, I made a connection. Awesome. Because if you roll the clock back, I suspect most of you had no clue what to write into grad student application. At least I didn't, I admit it. If you're a new student, you might not be feeling that. Anyway, I'll go on about this. So it's like, that's great. I have this connection. He says, processing digital video. That's exactly what's going through my brain at that moment. I know what digital is. I'm trained in electrical engineering. There's analog and there's digital. But video, like, wait a minute, I've never thought about how you process video, but that was never in my signals and systems classes. You know, video, how do you even encode video? And you know, so the brain is then starting to race, all right. And then he says to steer a car down the road, all right. And at this moment, that is what's going on inside my head. Okay. Like, that's science fiction. What are you talking about? You're saying there are actually people doing this and you have a student doing this and you've been directing to do this. So he asked me one critical question. Remember, I also said with this going on in my head, I am sure I am not a good poker player. So I'm absolutely sure this is going on completely clear on my face, but it's old school phone. If this had been a Zoom interview, I think he'd have flushed me right there. All right. So anyway, what was he talking about, Alvin? If you haven't read this paper, my advice to students is go back and read the paper. Pick any of them. Dean is a very good author, simplified at the particular one that I had at the bottom of the slides here. It's remarkably readable. And when I think about people who are so excited about tech but aren't disciplined in it, I point to this paper. In fact, I should have been doing this all along. Very clearly says I have this many examples. That many examples were not enough. I have this technique to amplify that number of examples. I have a disciplined strategy for doing this. And it's like, really? In 1980, whatever it was when this was first going on, that disciplined thought around this, it's like, oh, wow. techniques, discipline in the engineering and the science that we're applying, even as we're pushing the limits of this. Of course, that was NavLab 1. We saw the videos of that. So when did I actually start doing something in self-driving? I can say, well, my first opportunity to do anything was here on NavLab 2, but it wasn't me. Jenny Kay, Chuck, you mentioned it yesterday, was working on some teleoperation, not remote steering though. Click on some points, give the robot a path to follow. Well, this was in the early part when she was just getting started with the user studies. And she said, yeah, I need somebody to help go out. Fraser was in the front seat. She was sitting beside me. And I was literally in the truck that I'm trying to teleoperate, which is a little bit weird mind concept. But then you start clicking on the points and you're suddenly like, wait a minute, what exactly is going on? And the truck is starting to weave and doing this. So that was my illustrious role at doing this inside the NavLab. That paper is pretty interesting too. I actually went and looked for several different papers, and I was then reminded by the difficulties of writing papers and finding good figures and graphics. That graphic appears in like 4 years of papers. Like literally, you could just keep finding the same one. I mean, student-wise, remember, that was used to be extremely difficult to get any graphic to look right in a paper. If you got one good one, reuse that sucker. Much easier today. All right, so what were my early observations about self-driving in this case? First, these people are all really smart. This problem is super hard, and you need to know so much more than my one little part of the problem. All right, we were talking about it yesterday, a lot of you showing large team photos, massive multidisciplinary parts. What was my reaction in grad school? I think I should stick with stuff that does stationary cameras. All right, and if you know my work, virtualized reality, a dome of cameras. There were a lot of cameras. Turns out there's its own systems headache when you've got 51. They weren't digital. Analog VCRs that then had to be digitized. If your faculty advisors, by the way, are telling you to do things like label data, that's probably the modern equivalent. Back in my day, it was, okay, unbutton your shirt sleeves. All right, pull out a VHS tape, go put it into a digitizer system, and repeat 50 more times so that you can get all of your video. Yeah, so but it felt manageable. The world wasn't out to get me. There weren't, the negative obstacles. We had our good discussion on that yesterday. There weren't. Tony had a good photo of moss or some type of grass growing on a big boulder, and you're like, wait a minute, that's cruel and unusual punishment for off-road robots. This felt manageable. So a few lessons coming from this self-driving at the end of this stage now. It's still very cool. That's important in my career direction, clearly where I went. VASC, the autonomous systems part of this. Neural networks are cool. If you look at the No Hands Across America run, that was not actually with Alvin, that was with Ralph. I loved the naming trends. Where's Rahul? Oh, yes. You continued that kind of characteristic. I never picked that up, this ability to come up with these really clever names with these acronyms full of wonderful naming conventions. But I remember looking at this, though, and my conclusion in this era was that neural networks in the shallow style were very cool for helping you figure out what might be useful to your data. And the conclusion in that era was once you figure out what it's doing by looking at the nets, looking at the pattern of weights, is then go back and come up with an engineered solution that's typically 10 or 100 times faster, often very easy to understand, and yeah, okay, that's what you use these for. Boy, that's not a very modern interpretation, but in that era, if you look at the whole academic research community, it was the hinterlands at that point. Neural nets had reached their zenith, and then it was like, okay, that's a good technique, put it in the toolbox, and it just helps you do that. Of course, the cameras I could get at the time, and I could see everyone else, were still not the cameras we wanted. 320 by 240, 640 by 480, interlaced video, security cameras typically, and I go, this is a problem. 3D from imagery, a lot of my thesis work, it's like this is actually a hard problem. Who was it you were yesterday? Some of you were recounting the original statement of, well, now that we have this AI systems going, let's get stereo solved in a student project one time. Yeah, that's not so easy to do. There's got to be an additional way to get this data. I hadn't worked with anything else other than that, but Also at the end of the 90s, as I'm graduating, at that point, I really wanted to apply my work. It's like, okay, do you want to go pursue a faculty job? Do you want to go into maybe a corporate research lab? It's like, no, what I want to do is find a way to apply my ideas. And after one little startup where we said, yeah, let's go for it, using some of my work for my PhD, it was like, oh, I see. Yes, if it's 1998 and you're defending your thesis and you can show something that even remotely looks like a photo, well, let's call it an artist's rendition of a photo. You can say photorealistic, you get your PhD, you sweat the bullets, you get your faculty committee signs off. And then when you turn it into a company, you go, oh yeah, I guess my mom and dad would never have called that a photorealistic video. So what do you do? And I look around, and at least at that point, I couldn't find what I wanted, which is how to apply this in commercial sector, make actual sustainable business enterprises out of this. So, but I asked myself in 2000, I want to go to work in the most applied vision organization I could find in the world. That didn't go where I thought it would, because I'm like, there's got to be a company that's doing this in a real way. I at least didn't find such a thing. So Tony and John Bears, who's director, Tony was the associate director of NREC at the time, said, well, come on to NREC. Actually, we are trying to do that very thing in the thing that you've been avoiding your whole academic career so far, which is, yes, your cameras are going to be moving on you. All of your sensors are there. So welcome to autonomous systems or self-driving, embodied AI. How about for a modern term? You guys did not use embodied AI. I remember the discussions with Tony multiple times talking about the AI winter. He's like, AI was kind of the bad word. How many of you avoided using that phrase for decades of your life? Yes, exactly, hands going up. It's like, oh, now it's all in vogue again and we get to rebadge it, and then we get, I love it when I'm talking to an investor who says, yeah, but what about all this new stuff, this AI stuff? Oh yeah, I love that. That's the greatest thing, and we're right there with you. I'm so glad this new AI stuff is like, all right, great. So that led to 15 years at NREC. I didn't include videos. I knew some of these others were getting covered, and technically where Marshall was like, come on, try to focus on the on-road part. I'm like, but my CMU existence was off-road. Or in the air, or in the water. Basically, I had the privilege of working with a number of people and collaborating. And if it rolled, walked, crawled, floated, or flew, I was part of a system, a team, developing some prototype, pre-production, fieldable robots, typically at NREC, trying to get them into, out of the lab, where you might get that 1 out of 10. It worked. As so many of you know, making it actually work most of the time so that they can start to see the applications that whoever it was wanted to do. The DARPA active one was one where I was really, really disappointed. It was nearing the end and I was leaving, and I had to send Jeremy Searock, had to send him. He got to go actually see the real boat that got built, and I'm like, it's a 100-foot boat? Seriously? Oh, shit, I don't get to go. This is not fair. The Sikorsky aircraft, I really wanted to do some of the automation on the Sikorsky. Didn't get to do that part, but it's actually carrying a ground vehicle in the lower right corner there. That was an interesting one. To fly a ground vehicle in a couple 100 miles was the idea, and then deal with whatever you needed to do at the remote location. And just all of these things. The TARDEC, actually the LS3, the Legged Squad Support System, not nearly as clever as the naming of Alvin, Ralph, and you had Chipmunk. No. Raccoon, that's it. All right, yeah. All right. But LS3, that was neat working with bigger than Big Dog. I remember Al Reezy was there, and he said, don't call it what is coming to mind. And I'm like, he's like, all bovine analogies are stricken from our vocabulary. So, but that was a big robot that could carry 400 pounds of gear for the Marines. And my one and only trip to Hawaii, which I envisioned being much more joyous. All of you know in field robots, you don't go to the oceans and the shores with a robot that walks on the ground. No, you go to the middle of the islands and you find all of the nice red dirt. And then when you show up in the evening or however late it was, at the hotel, oh, Dave, yes, you're here. Yeah, you remember how we attempted as best we could to get that off our boots and not get it into the hotel lobby. Yeah. But the Tardec one up there on the cargo vehicle was interesting because that was later stage and actually getting into much more relevant military operations and convoys and getting on vehicles. And it was a neat collaboration. Tony mentioned yesterday, Tom Pilarski are no longer with us. We're all mortal, and you suddenly realize a man of your own age is no longer with us. You go, oh, appreciate the times and the experiences that you have. But we were able to work together on this and really advance the idea of robots beyond just the convoys that had been, and getting this into fielded was inspiring to me in so many ways, and began to remind me of why I went there. It wasn't just another cool prototype, it was production. But okay, 15 years, what were some of the lessons that came out at this point? Fieldable prototypes absolutely require cross-functional teams. You can, and you know, the new lesson though was that as these teams get larger and as you start working with commercial partners, rather than everybody in my grad days, it was all internal. Everybody at CMU, everybody all in. We know it's all disruptive. 15 years at NREC gave me the opportunity to see the difficulties that we had in trying to get the corporate partners to understand what would need to happen and how much, when you're frustrated, you call it hand-holding or aggravation or drag. When you take the long view, though, you realize that's called investment in relationships and education and actually opportunities, as I'll get to in a minute, to learn some other things. But it's vital. That team dynamic must work. If the team dynamic isn't working, you're never going to solve the complex levels of problems that we have. Productization needs a real business case, all right? At this point, looking through this at NREC, so many things were technically possible. I could make a product that could do this. And NREC, we definitely got the chance to see much more of that product focus. But to make it economically, to turn it around and say, how can it actually become a sustainable part of a profitable enterprise? That was hard. And in fact, at that point in time, even as until what happens next in my life occurs, I didn't understand how self-driving cars would ever make it. As Dirk talked about yesterday, he said, you know, if you really, and speaking from a traditional auto view, which is the only view I thought of, it was, there you are, it's like you've got to get a price point down to be, what, maybe 10% is an expensive feature option on an automobile. And I go, yeah, but the autonomy costs more than the car. Like, I don't know how to sell that. It's never going to work. I don't know. Sensors. This is a little bit more on the technical side, but sensors are still frustrating. The pixel counts are too low, the dynamic range is insufficient, low light sensitivity stinks, range for LiDAR too short, everything is too expensive. Nothing is focused on my application. It's still borrowing sensors from other domains, targeted with other product requirements, and we're all getting by, but we can't really get what we want. And computing is still ridiculously agonizing for reasons you probably perfectly understand. All right. What's interesting at NREC, though, and doesn't get as much attention, I wanted to call this out a little bit, is that we were actually advancing into the productization in levels that most people really hadn't heard about. So I highlighted two of those efforts here. One of those was the autonomous navigation system, part of Future Combat Systems. Future Combat Systems was a multi-billion-dollar a year effort by the federal government to revolutionize the way we fight wars, the way the Army would go to war. It was, until this program, everyone knew you needed armor. The goal of this program was find a way to deploy in 48 hours forces that normally take 48 days. To fight forces, which means you need to, in order to do that, you need to lighten the force, you need to deploy by air, you're not going to have the armor protection, so you need to find an alternative way to go, which ended up being a network-centric warfare system with a lot of communication, but you also needed an autonomous angle. While the program was a couple $1 billion a year, it was I don't know, $250 million Can you imagine if you can roll the clock back? That was a huge program, and it seemed like an unbelievable sum. And don't worry that we need to put it on every variant of every vehicle that's out there. I know it's like 11 different vehicles that we're building. You can build it. It's all one autonomous navigation system. That was the kind of goal. What was interesting, though, is now we're getting past the science part, as Drew said, and getting into the application. We're also getting into the safety engineering. That's a whole new can of worms that we just didn't have those skills in. And it brought me into contact with people like my co-founder at Argo and now at Stack, Brian Selesky, is this young guy who'd spent only a couple of years in the train industry. But when he talked about the scariness of typing at a keyboard to say, okay, I'm about to activate something that changes the way the train control system works, and it's on part of the tracks where we're dark. It's called dark track because we don't know where the trains are. You must keep strict monitored documentation and active state that says what trains entered, and not allow somebody else to go the other direction until you positively confirm at the end of what could be hundreds of miles of track that they've left, and then reauthorize that. And he's like, when you're sitting there and you're typing at a keyboard and you're about to hit enter to bring it live, you're like, oh shit, did I really test everything the way I should have? And what were the techniques that he began to learn about there and could bring in that kind of expertise in the production software engineering that went in? That was the kind of thing that was going on. The other part of this the program that Brian, Drew, a few others worked on was the CAT hull system. They call it CAT MineStar Command for Hauling. CAT MineStar Command for Hauling. That's not exactly what any of you would probably ever have imagined calling your autonomous truck, dump truck, 400 ton, you saw the photo. The latest information, and I just found a press release, Drew, they're up to over 9 billion tons of ore that have been hauled, hundreds of vehicles. What's interesting to put these two in contrast is that the budget for that haul truck was dramatically lower, but the problem was ridiculously focused by comparison to what we were trying to do on ANS. And no surprise, all of you know, if you try to do everything, you often end up with nothing. So after 7 years, the ANS program, one of the last things that was still alive from FCS, they eventually said, budget crunch, that was how AHS ended. They said, we're funding an autonomous navigation system to go on no vehicles anymore because we've terminated all the vehicle programs, and we sustained that for about a year afterward as we began to try to look to deploy on current force vehicles rather than future force, and said, all right, but it's time, cut the plug. All right. Whereas CAT, by focusing the problem still, big enough to be useful but small enough to manage it, actually found their way through and continuing to operate. So what does that get you to these lessons? Too much scope can kill products. Got to be aware of that. Some points there. I won't go through. I guess I'm probably talking too long. All right. Focusing products help, and the safety case takes cross-functional training. You know, things 882D, I don't know what it is now, E, F, G, 26262. That was just like it could have been a hex code as far as I was concerned in terms of my understanding. All right, but those are military and commercial spec numbers for safety engineering and functional safety. The concept of SOTIF, safety of the intended function, the ISO specs that go along with that they're only very recent, just in the last few years, finally getting standardized. This concept of safety engineering is a critical pathway to the deployment of anything that has the safety ramifications of self-driving vehicles and trucks. We didn't have it, and the community that knew it had no clue how complex self-driving vehicles are. They wanted to go through and run every test case, you know, maybe several times. And it's like, do you know how many pixels are in a single frame and how many times per second we do? Like, you can't reproduce every single possible input and test it. And so how do we actually go about making sure the core function of the components is working? Got it. How do we make sure the system is functioning? Like, oh, that's where SOTIF has evolved. And these two groups that were so far apart quietly began the work on those two programs and in others, but from my experience in those two. which eventually then led me to Uber with Drew and 50 other people from well, maybe not quite 42 from the university. Poor Marshall. Yeah, sorry, bud. Why did we all leave? There was the note I said that in 2000, I wanted to apply work, but I couldn't find commercial, so I'm at NREC. Then there was the note that I still didn't have a business case for self-driving vehicles. And John Bears, I get under NDA, and he was already in and on the inside trying to form enough people to get critical mass to say, yes, let's do this. And I signed the NDA. He says, here's what it is. Uber wants to do self-driving. And I'm like, all right. The classic pattern was another stupid company that knows nothing about the tech, thinks they're going to throw a little bit of money at the problem, and in 9 months they're going to have a product. And like, I'm the first one to ever thought of this, right? And he's like, no, they're actually throwing ridiculous money. When I throw them numbers, they say that's not enough, there's more. I'm like, but why? I still don't get it. Fine, they have money, they have passion, they clearly know how to raise more money. He's like, Pete, we've been viewing the business problem entirely wrong. You've been focusing on personal ownership, but if you operate a fleet of vehicles, you suddenly look on a return on investment. I'm like, huh? Uber wasn't really much in Pittsburgh. All of my testing took me so far out, I just hadn't used it, literally, at that point. He's like, here's how it works. People pay a couple bucks a mile to get driven around. All right, if we can get 250,000 miles of lifetime out of a vehicle, that's $500,000 of revenue for a vehicle. He's like, now I know our vehicles are expensive. Suppose it's a couple $100,000. I'm like, but he's like, for the first time ever, I actually see a number that's left that's still in the black. There's a lot of other costs, but that was the fundamental revolution that took so many of us to go, God, this might actually work. And there's big money that can actually do this, and it's going to take it. So I lasted about 20 months at Uber, helped to get that first prototype out. Neither of you showed the Volvo, or did you? No, because you were off-road yesterday. Anyway, I deleted that from the thing, but I missed that. After 20 months, Brian was getting agitated at Google, saying they're never going to do what they need to do. They're on a technology quest, but in order to actually make money of the style I'm talking about and pay the salaries of a massive engineering staff, is you need to scale. If you're going to scale, you need a manufacturing partner, and Google at the time was not interested in partnering with anybody with any terms that any OEM would have accepted, and none of them did accept, and they approached everybody. We knew at Uber because when we went in and talked to them, they were all complaining about how absurd the terms were that Waymo wanted, or Google at the time wanted. So Brian and I said, let's start Argo. Let's go for another way. Let's tightly couple ourselves to Ford first, and then eventually brought in VW. That may have not worked out as well as we wanted. When you get two competitors together and in established industries, then they, at some point, having made the deal, they suddenly realize, wait a minute, we have to be careful about antitrust. And then your board meetings are like, well, don't tell us what's really going on about numbers or volume, because then I can figure out your numbers. If there's only two, total minus mine equals yours, and that's somehow anti-competitive. And anyway, interesting. I won't go into all of that, but also had a chance to fund some work at CMU. Not a lot of people know a lot about Argo, though. So if you go back to the internet Wayback Machine, you pull out data. This is how I got all this, to make sure I didn't take anything with me. Didn't want Ford or VW pissed. But if you go back, we're actually operating in 8 cities. These are the actual maps that we had at the time. As we heard for Cal, the mapping technologies that you're using probably have stepped a little bit beyond, but a lot of the same kinds of ideas to build your own maps, to do this efficiently and cheaply, and actually get out there. And mapping a city, it's not a geographically large area compared to U.S. country, but you start counting road miles, and you're like, wow. And when you count things that are expensive to model, intersection counts, Miami, in certain areas, there are 20 blocks per linear mile of a single, or it's 20 blocks, 20 intersections then. And some intersections in Pittsburgh and Miami and others are not nice 90-degree things. So tremendous ability to get the mapping and vehicles and scale, because, again, if you're going to actually make money, $500,000 in that analogy sounded great, but go try to cover a what is the, let's say this, many hundreds of $millions a year burn rate for the larger companies, Argo among them. You realize all of that NRE, you have to get a large fleet of vehicles to eventually make that, to cover that whole thing. And so again, on scaling, it's I need enough vehicles, I also need enough territory to pump them in. If I don't pump them in fast enough and soon enough, then I keep losing money year over year until I finally get there. All of that operation was scaled up nicely. And now we'll see if I link the video well. Yeah, all right. So what we got to about 6 months before Ford and VW decided that they didn't want to. Driverless operations in 2 major cities, in Miami and Austin.
First driverless vehicle.
Oh my goodness.
Available.
Confirming the ride.
Matched.
There's no driver. I mean, it's so exciting to be able to be in the car, to see it driverless. It really does feel very natural.
It's driverless, Brett. It's really driverless.
Driverless.
Just watching that wheel, and there's nobody here. This is crazy. This is amazing.
No driver.
Great job, car. Do I tip the car? All right, Courtney.
Driverless rides in a major city in daytime, and here we go.
So we got that far, demonstrating, developing a safety case around that, getting to the point we have all of this capability, doing this in 2 cities. We didn't die for technical problems. We died because we didn't have enough capital, all right? And 2022 was a very bad year for fundraising, if you go back. That was when all of this was coming to a head. Am I out of time? Hold on. No. There we go. All right. Now I started Stack, certain competitors. All right. We haven't said much publicly, so next slide. Final topic I wanted yesterday, and one of the reasons why my slides were even later than they normally are, was that I got into the office, in a rare moment where I went into the office Wednesday morning, and I suddenly had an idea. I didn't have enough lessons yet, but there were certain themes that I wanted to do, so I started to scratch at a whiteboard and said that wasn't readable. And then I put this together and said it's still not readable, but to highlight a few dimensions, if you look at the evolution we've been going through I started in the 90s. That's when my experience starts, 91, right? 90s, 2000s, 10s, into the 20s. If you look at some major categories, it's so bad I need to pull out my own reading glasses to read my own slide. If you look at some of the headline programs that are there, you can see us moving from inspirational demonstrations into serious commercialization and 150,000 rides a week for Waymo. You can see the sensor hardware actually evolving into the point now, or if you start now, a company, say in the last year or two, wonder who did that, you find a lot more off-the-shelf components that is actually targeting. Like you can get an 8-megapixel camera with 140 dB of dynamic range, seriously? And then it's auto-grade, like with the Roper connectors, and like, holy shit, this is amazing. Compute hardware, we didn't count tops, all right, but look at the evolution there. If you look at the perception approaches, you can see significant changes. It isn't just the hardware components that have helped us. There have been some fundamental breakthroughs that we alluded to. Remember when deep nets, we could finally do this, and transformers and foundation models more recently. The curation of data. Anyway, this to me is an interesting kind of way of framing the problem. This probably isn't the best slide, but if you really want to get good historical view on what's been going on and how it's evolved, this table feels like the kind of structure that might be an interesting thing for, if Richard Bishop is here, he can probably do this 1,000 times better than me. But some of you, it may inspire you also to think about what happens in the 2030s. So, okay. All right. There I will, since you want to ask questions. All right. Thank you. Okay.
All right. Stay there. Yeah, go ahead. So we want to stay on time. So in the interest of time, I'll just ask 1.5 question, and then we might take 1 question from the audience as well. So here is the 1.5 question. The good news is that the technology is so mature that it can be moved to the real world to those companies and the great things that you describe and that, of course, others do in other companies. So that's the good news. The bad news is what do we do now in academia, in universities? What is the role of research in universities moving forward in this field, if there is a role? And by the way, the role cannot be staffing Uber etc. Just to be sure, okay? You understand the question. And the one half question after that is what, at CMU in particular, what can we do better to help in that future development of technology and remaining involved here? Your turn.
I think that's a great question. I do actually have an opinion on it. And I think it's a combination of a couple things. I was not here for the founding of RI. I was not here when that happened. But the impression I have of Carnegie Mellon, both in my time and before my time, was that it was very entrepreneurial. If you, as a faculty member, wanted to make a thing happen, you could build a thing. And I'm very close to falling off the edge, yes. And that I think that is a key to success in academia, is you have to have people like Raj who are willing to go build a thing and build the next thing, right? And so, yes, I think there's interesting work in self-driving to be done in universities, but I think also what universities really succeed at is building the next thing, the thing that's not commercial yet, right? The industry is great where there's a clear business objective to be met. I think where Carnegie Mellon can really succeed is finding those things that don't yet make sense and really pushing that. And I think the more grassroots it is, from faculty members creating that thing themselves, the better. That would be my answer.
And I would support that. Within self-driving, Raquel mentioned, wherever she went, anyway, yesterday, talking about economical, sustainable AI. She had a term for it, whatever. You know, when it costs $1 billion and an unbelievable amount of energy just to train models, that's, oh, there you are. We know that is in creating an economic barrier. So opportunities, and we're no different with the demand for data right now. You said exactly what I feel is like it's going through the roof. I want more data. I want to train on that data. Can we get techniques that are actually far more data efficient to achieve the same level of performance? You want to see another company get formed or see a current company change its internal tech approach? Come up with better strategies to be able to do more with less. Be more efficient in what you're doing. Save 1% on $1 billion budget. That's like, wow, that's a big number. Save 10%. That's huge. Make it go 3 times faster. Wow, transformational. So I think huge innovations there. It's also clear that core, actually Zico is getting more applied. And I go, wow, who thought that the core ML, like all of the real theory side wants to get applied? It's like, well, because at times it's because of an algorithm innovation. You know, when was the big paper about actually being able to properly train a deep net and not have it just get lost and do that? What was it, 2014? You know, when did transformers really hit? What was that, 2017? So the algorithmic innovation going on is radically changing our ability to deploy today. I think that continues to be it. In addition to finding whole new applications, as you said, yeah.
All right, thank you. We have time. If there's one very quick question in the audience, we'll take it. Otherwise, we'll move on. Yes, Raj.
One of the metrics we used to talk about is 40,000 people are dying in the United States. With this technology in place, we should be able to reduce it by 80, 90%. Do we know where we are with respect to that? And how do we measure it? How do we get there?
Yeah, can we improve? Yes. Do we have enough data to prove it? Waymo is beginning, so they're the most public at showing that they believe they're substantially further ahead. How far ahead? I don't know whether everyone is doubting, I would say, in the broad community. Is Waymo being authentic and accurate? What are they not telling us? There's a natural cynicism. But their evidence is pretty compelling right now that it's multiples better.
So one suggestion is we can have a movement saying every car should have autonomy built into it of some sort, and it should take over when things are going to get bad. Otherwise, let the drivers drive. So, some way of proving this technology will not only save lives but also save a lot of money.
Yeah, I think that makes a lot of sense. I think that's a product a little further down the road. I'll also observe that many systems right now are sort of the reverse. They drive until things get bad, and then they want you to take over. So I think that that kind of level 3 isn't there yet, but I think it's an exciting future too.
Okay, so we're going to close the session. I would just note one thing between the thing that Drew showed, the one picture that flashed, and the presentation from Michael yesterday. If the entire problems of the trucking industry in the US is not solved by people in this room, I don't know what to do. Okay? All right, thank you.